Kartikeya?
Yes, sir, it's visible, sir.
Okay, thank you. Yeah, in the last class, I guess we started discussing about differential amplifier and its characteristics. Today we'll talk about the what you call other version of differential amplifiers, differential mode of operations. What we, I- if I guess what we were discussed in the last class was that the RD value, that is the load resistance that you're going to connect, which should be less than the twice of VDD minus VCM plus VTH divided by ISS. This was a formula that we arrived considering a differential amplifier where the RD is going to be limited with this expression. So you have to fix the value of RD here, and you cannot go increasing the value of RD because for a given value of your ISS and VDD, VCM and VTH, your RD value is going to be fixed out, because if ISS is fixed and VDD, VCM are, these parameters are going to be fixed, then you cannot vary the value of RD, because there is a relation which indicates that RD value should be limited. And if you fix the value of RD, and as you notice from the gain formula, then your gain is limited with RD, because AB, which is equals to minus GM times RD. So RD value is limited, then your AB value is going to be limited. So this is treated to be one of the limitations for your differential amplifier. Now let's take an example here, and then we try to analyze what is the value of RD, how it can be. Let's take a differential amplifier with a common mode signal VCM. Let me draw the differential amplifier here. This is the differential amplifier, which consists of two transistors M1 and M2, right? And these two source M1 and M2 source are connected to a current source, which is referred to be ISS, and both gate of the transistor M1 and M2 are connected with a VCM signal, which is referred to be DC signal that you are applying, and both the transistor gate terminal is connected to VCM. And here this is referred to be your VDD, this is RD, and this is your RD of a transistor. This is how we define the common mode signal that we are applying for your differential amplifier. Now, if this is our circuitry, then the values were given to us. The value of your VCM is 1.6 volts, is the VCM value which is given to us, and the value of ISS, which is limited to zero point 0.5 milliampere, is ISS value, and threshold voltage of the device, which is given as zero point 0.5 volts, and the supply voltage VDD is given as 1.8 volts. Now with this, we have to identify what is the maximum value of RD that we need to keep. So now if you use the formula for RD, that should be less than twice of VDD minus VCM plus VTH divided by ISS. And if we substitute the values here, what you can see is VDD is your 1.8 and VCM is 1.6. So you'll get 0.2 plus VTT is V threshold is your 0.5, so 0.7. And ISS is your 0.5 volts. So 0.5 is treated to be like 1 by 2, and then 2 goes up, then it is zero point 0.7 into 2 is 1.4, and milli will goes up as a K, and here twice is there, so what we'll end up with is 2 into 1.4 K, which is RD value, and should be less than that. So you'll end up with getting the RD value is definitely less than 2.8 kilo ohm. This is RD value that you need to choose for your differential amplifier for this kind of signal which is available to you. So you cannot increase the value of RD as you wish to increase the gain of amplifier. Okay. So we had seen that your what do you call, RD is limiting your gain of amplifier, and then other parameter GM is also going to be limiting with your gain of amplifier. Now what we discuss is that we try to discuss the differential mode of operation of your differential amplifier. what you can call it as differential operation. It means you are not going to apply the same input for both the transistors. You apply the different input for two transistors, right? Differential operation. Now we apply the different inputs to this differential amplifier and let's see how its performance is going to be varies. Let me draw this differential amplifier again. I'm not drawing the symbols accurately here because my pen is not so, you know, accurately drawing the structure. Then, but you have to draw it accurately. Resistor symbol as well as your transistor symbols. And this is ISS. Now here we are applying differential input VID, positive and negative. And here this is referred to be your M1 transistor and M2 transistor, RD, and this is RD and VDD. Of course, we have two outputs which is referred to be VD1 and this is your VD2, right? Now, what we are trying to do here is that, you know, if this transistor, M2 transistor is under saturation region of operation, M2 transistor specifically this one, if this is under saturation region of operation, then you have the current in your device and that current is referred to be your ID2. We try to operate it basically, right? We'll make M1 and M2 are under saturation region of operation and correspondingly we have the current in both the transistor is ID1 and ID2. And with that ID1 and ID2, we can easily identify the value of VD1 and VD2. But here we are applying the differential input to both the transistor, means the input we are applying for M1 is not equal to the input we are applying for M2. If M1 is a different value and M2 is different value, consequently what you can see is that the current ID1 is different and ID2 is also different, right? So what you can write it here, the current ISS which is equal to ID1 plus ID2, right? As the total current is equal to ISS, but this total current which is equal to sum of the ID1 plus ID2. If one of the current increases here, ID1 increases, because ISS is constant, then definitely ID2 is going to be decreases. Or else reverse is ID2 increases and then I1 decreases and finally the total value is equal to ISS. Okay. So whatever the operation you do, but the net value of ISS remains same. Okay. Now let's see if we connect M2 of a transistor, to ground. Okay. M2 of transistor nothing but M2 of a M2 transistor gate terminal is connected to ground. And what you can notice here is that the gate to source voltage of the transistor here M1, which is this one, VGS1 gate to source voltage, and here for M2 VGS2. Okay. As we are applying the differential input here, if we apply the differential input which is referred to be VID, right? Then what you can consider that VID which is equal to VGS1 minus VGS2 is not equal to 0. If both the inputs are same, then definitely VGS1 minus VGS2 is equal to 0, but we are applying VDID which is not same at gate to source voltage of M1 and gate to source voltage of M2, which makes that this is not equal to 0. And we consider the situation for the diagram which is shown over here is that VID is VGS1 is greater than VGS2. Okay. It means here it is not equal to 0. What you can consider, it is greater than 0. And now consider the case here, VGS1 is greater than VGS2, because the connection will shows this configuration here. Okay. And as a result of that, what you can write it here is that ID1 should be greater than ID2. Okay. As ID1 increases, then ID2 is going to decreases because VGS1 is higher comparison with your VGS2. Okay. but net value of your ISS remain same. Now if we take a plot here, considering this factor, what we are going to plot here is, I'll take x-axis is a differential voltage which is at V input 1 minus V input 2, means this input voltage and this input voltage. Okay, difference of these two. This could be 0 or this could be positive and this could be negative. This is a point where this is referred to be 0. What it means? It means that V input 1 is equal to V input 2, and as a result of that you will get the differential input is equal to 0. So both the inputs same. Then when both the inputs are same, then VGS1 is equal to VGS2. As a result of that, what you can see is that ID1 is equal to ID2. Okay, you will get same current because VGS1 is equal to VGS2. And if that is the case, then what is your ID1? ID1, which is equal to ISS by 2, and ID2 is also ISS by 2, right? At V input is equal to V input 2, V input 1 is equal to V input 2, which is the differential input is equal to 0 case, then the current in your differential amplifier and ID1 is treated to be ISS by 2 and ID2 is treated to be ISS by 2. Let me consider this y-axis. This axis is representing the current I. Okay, but at differential input is 0, then you have the maximum current, that is this point I can consider, and which is your ISS by 2. This is your ISS by 2. Okay, and what is the maximum current that you can see in a ID1 or ID2? But the configuration which is shown over here is definitely ID1 is greater than ID2. What is the maximum value of ID1? If ID2 goes to be 0, then definitely ID1 is becoming ISS. Consider that ID2 is equal to 0. What it means? It means that ID2 is connected to ground, sorry, VGS2 connected to ground, VGS2 connected to ground, and VGS1 is higher value. As a result of that, ID2 goes to 0 and then ID1 is becoming your ISS. Right? So the maximum value, I can write it here, this is a maximum limit which is referred to be ISS limit. So now let me consider this is the ISS limit and this is the ISS by 2 limit. ISS by 2 is the current when both the inputs are same. Right? Now when VGS1, now you can consider this is a point where the V input minus V input 1 minus V input 2 is 0. As this value is becoming positive and higher, what it means? V input 1 started dominating than V input 2, and that's how you will get the positive value of differential input V input 1 minus V input 2. Right? So now V input 1 minus V input 2 is higher, then what you can see is that ID1 current start increases and ID2 current start decreases. Am I right? Yes. So what you can write it here is the ID1 current is going to be increases here. So let me consider that it is going to be increases slowly as your differential input is going to be increases. As it increases further, then what you can see is that the differential current is also the ID1 current is also going to be increases. So now this is referred to be your ID1 current. ID1. As ID1 increasing, what happened to your ID2? ID2 is going to be decreases, and then this is how your ID2 is going to be look like. This is the ID2 current when V input 1 minus V input 2 is becoming larger value. Right? So V input 1 minus V input 2 is increasing and its value positive, then this is how the current ID1 and ID2 is going to be varies. So ID1 becoming ISS, ID2 becoming 0 value, but at the differential input is equal to 0, that is V input 1 minus V input 2, then ID1 is equal to ID2 is equal to ISS by 2 current. Right? Now, if we try to draw the VD1 and VD2, means the drain voltage at the transistor M1 and drain voltage at the transistor M2. Okay, that we are going to plot now. So here I can take the x-axis remains same, which is V input 1 minus V input 2, and this is 0 point here. Okay, Now at V input 1 and V input 2 is equal to 0, then maximum current is referred to be ISS by 2 in both the transistors M1 and M2. ID1 is equal to ID2, which is equal to ISS by 2. And correspondingly, the voltage, so this axis, y-axis of this plot, so this is your y-axis, and which indicates the voltage as V, okay, which is VD1 and VD2. So at V input 1 minus V input is equal to 0 case, then what you can notice here is that you can notice that the current remains same, and then voltage that you can notice here is that this voltage is referred to be VDD minus ISS by 2 into RD current in both VD1 and VD2. So this is the current where it is VD1 is equal to VD2, right? And which is at V input 1 minus V input 2 is equal to 0 case. But now, as V input 1 minus V input 2 is increasing and positive value, then your ID1 increasing, and as a result of that, what you can write it here is that VD1, which is equal to VDD minus ID1 into RD, and VD2, which is equal to VDD minus ID2 into RD. So as your value of V input 1 minus V input is positive, then your I in 1 is going to be increasing. As I in 1 increases, then what happened to this VD1? So now you take VD1, and here ID1 is increasing, and the drop here is going to be increases, then net value of VD1 is going to be decreases. So now this is how your VD1 is going to be drops. As it become higher value, then your VD1 value is becoming lesser and lesser, and it becomes 0. So this is your VD1, because ID1 increasing, the drop across this ID1 RD, the drop of your ID1 RD is going to be increasing from your VDD value. So net value is going to be on this one, and it is not exactly 0. This value is going to be the minimum value that you can see here is that VDD minus the ID1 value is maximum value of your ID1 is ISS. So this is your minimum value of your VD1. So this is a minimum value. What is this value? This value is VDD minus ISS into RD value. It is not exactly 0, because the maximum current that you can notice from your transistor 1 when V input is much higher and V input is equal to 0, that case your ID1 is ISS, and the drop, the voltage across your VD1 is becoming your VDD minus ISS into RD, and this is what the value. So this is your VD1, right? So this is your VD1. Now VD2 is going to be increased here like this, and then maximum value that you can notice here is that this is the maximum value, which is as your VD ISS is going to be becoming 0, ID2 is becoming 0, then net value is going to become the drop value of this two, this one is becoming 0, and then you'll end up with the value called as VDD. So here this is a maximum value that you can see as VDD, right? So this is what the current as well as the voltage at ID transistor drain terminal of your transistor M1 and M2 respectively. Okay, these are the current at transistor M1 and M2, and these are the voltages. So this is your VD2. VD1 and VD2 are the voltages at drain terminal of M1 and M2 transistor, right? Now we are considering the positive side of V differential input, which is V input 1 minus V input 2 is 0 and positive, right? Now if it is the reverse case, means V input 1 is less than V input 2, then this value will become in the negative, obviously, right? So if this value is negative and smaller, then what happened to your ID1? ID1 is becoming lesser value and it starts drops. So ID1 start drops here slowly, and it becomes 0, something like this. Okay, so this is your ID1, and then next your ID2 is also becoming higher value. So this is your ID2. So these are the current and differential input voltage plot. Now coming to this voltage VD1 and VD2 with respect to differential input voltage, then what happened to your VD1 here? So VD1 is becoming more value here and become the maximum. Whereas here VD2 is becoming less value and it's become the minimum value referred to be VDD minus IS into RD. Right? So in both the cases. Now what you can notice from these two plot is that now your differential amplifier is applying inputs from 0 to some value, and here at this point you can notice that your current is becoming saturated, either it is ISS or zero current, right? So when consider this ratio, now let me consider from this point to this point the differential input V input 1 minus V input 2, where your ID1 is becoming higher value and ID2 becoming smaller value, and it reaches to the maximum value of ISS and ID2 becoming 0. It means when your differential input within this limit, then your differential amplifier will respond for your input, and then after there is no change in your current in your differential amplifier, and then after there is no what you call variation in your output signal, means it cannot accept the, even though it accept it, but it cannot respond for your output signal because outputs become saturated. Current become constant, either it is maximum value or the minimum value, and then you cannot see any changes after this. So what we can consider here is that if your differential amplifier is responding to certain range of inputs from zero value to certain range, and this is referred to be called as range of a differential amplifier. What is the range of differential input at which the differential amplifier respond for the inputs? This is at the positive side and this is at the negative side, right? So this is the range limits from positive negative side to this positive side. Okay, 0 to positive value and 0 to negative value. Similarly, here also, this is what your differential output that you can notice with respect to the output voltage, and then this one is your with respect to your current, and this one is your with respect to your voltages. So what you can consider is that we need to identify what is the range of the differential input so that the differential amplifier is going to be respond. We have to know that range, right? So what we can write as ID1 here, the ID1 current, I can write it as ID1, which is half mu n COX W by L into VGS1 minus VTH whole square, right? What is ID2? ID2, which is equals to half mu n COX W by L VGS2 minus VTH whole square. Now, what we can consider here is that W by L ratio of your, both the transistor must be same. In some of the textbooks, what you can consider is that, this mu n COX factor can also be represented as Kn. This factor is also represented as Kn, right? And along with your Kn, what you can also notice is that this entire factor, that is mu n COX W by L, is referred to be beta. This one is referred to be a beta. So what we can write it here is half first transistor M1 transistor, that's why I can call it as beta 1 here. This is referred to be beta 1 VGS1 minus VTH whole square. Similarly, this one is beta 2 VGS2 minus VTH whole square, right? What is the maximum current that we are getting? We are getting the maximum current ID1 is equal to ISS for a given connection where your ID2 is becoming 0, right? What is the differential input that we can write it as VID, that is the differential input, which is VGS1 minus VGS2, right? What is VGS1 from this expression? This, you can call it as this expression. You can easily write it as what is your VGS1 value. So this is the VGS1 value. Now I can write it as, from this expression, what I can write as VGS1, which is equivalent to, now you take this term there, 2 times ID1 by beta 1, and then square root is there, then you take as a root, and then VTH of a transistor. So this is referred to your VGS1 of a transistor. Similarly, you can also write VGS2, which is equals to root 2 ID2 divided by beta 2 plus VTH. Right? Now what you can define is the differential input VID, which is equals to VGS1 minus VGS2. So now we can define the VID, which is 2 times, now let me consider it as 2 ID1 by beta 1 under root plus VTH minus under root 2 ID2 divided by beta 2 plus VTH, then it is a negative sign, then it is minus VTH. So this gets cancelled out, then you end up with getting the value of VID, which is referred to be under root 2 ID1 by beta 1 minus the root 2 ID2 by beta 2. And here the maximum differential input that we are talking about, the point here. So this is the point where the maximum differential input we are applying, and then after you can say that the current is not going to be varying. In this case, what is your ID1? ID1 is becoming ISS and ID2 is becoming your zero value. So if you write the same here, then ID2 is becoming, this is your ID2, this ID2 is becoming 0 at a maximum differential input. Okay, at maximum differential input, ID1 is ISS and ID2 is equal to 0. Now you substitute the same thing in the previous above expression. What you can consider is ID, which is equals to 2 times of ISS by beta 1 under root, right? And you might have heard the term called as overdrive voltage. VOV is called as overdrive voltage. Overdrive voltage is equal to be VGS1 minus VTH. Okay. So now if you consider that VGS1 from the above expression, what you can get is that under root 2 ID1 by beta 1 minus plus VTH minus VTH, this two gets cancelled out because same term, and you end up with VOV, which is referred to be 2 ID1 by beta 1, right? So what you can write it as, this is equivalent of VOV value, overdrive voltage. So what you can write it here, the maximum value, the differential maximum value that you are getting here is referred to be, this point is referred to be VOV positive, and this point is referred to be minus VOV negative. So these two are the values. Okay. And what is as minus VOV less than VID less than plus VOV. That is the range of your differential amplifier, right? Now, if you take this current variation with respect to differential voltage variation plot, means this one, if you take this plot again, let me redraw it again here. What I'm drawing here is that x-axis is a differential input, which is V input 1 minus V input 2. It's a 0 point, and the maximum current is here is ISS by 2 at this position, right? And what we can notice here is that the maximum current that you can get as ISS, and this axis will indicate the current I, and this is 0 point, and we are talking about this range VOD, right? This is your VOV overdrive voltage, and this is your minus VOV overdrive voltage, and this is called as the range of your differential amplifier. Now if I draw a plot here for this, then what I can write it as something like this. something like this, and this is becoming constant, and here this is what is becoming constant, right? Now what you can notice from this is that as your variation of the current with respect to change in the voltage, so this is x-axis which is change in the voltage, and this is referred to be current. So change in the voltage by current is referred to be your gm, transconductance. Gm we already defined as del id by del vgs. This is a transconductance, means this slope will define you the transconductance of your amplifier. And we are well aware that if transconductance is enhanced, then differential amplifier gain is going to be enhanced, right? And what we are going to notice here is that now we want to increase the range of differential amplifier. What it means? It means that instead of limited to this range, now we want to increase the range from this point to this point. Then how the plot is going to be look like? The plot is going to be something like this, right? Next, if we want to increase further, then it is going to be something like this. Then here it's supposed to be go this way and like this. This is supposed to be going this way, something like this. As you see the different color, graphs, then as you are going from first one to this is the first one, this is your second one, and this is the third one. As you are moving from 1 to 3, then slope of your ID versus VGA, ID versus V input variation is going to be decreasing. The first one which is having higher slope, and second one is having lesser slope than the first one, and third one is having much lesser slope than the second one. It means as you are trying to decrease the value, as you are increasing your overdrive voltage, then you are trying to decrease the value of gm. So one side we want to make our differential amplifier is more sensitive with your change in the more range of differential input voltage, but advertently it causes to be decrement of the gain of an amplifier. So you cannot go for higher value of VOL. We are interested to go for it, but the adverse effect of that is the decrement of your GM of your differential amplifier. As GM decreases, then your gain of final circuit is going to be decreases. Okay, so you cannot increase the VOV value as you wish because the GM gets affected because of that. Okay, so you require a differential amplifier that should be respond for larger range of input, but here the problem is that GM is becoming smaller value as you go for more range of VOV values, right? And now we'll see the small signal model for this differential amplifier. Okay, so this is about your differential operation of your differential amplifier. Now we'll see small signal model of your differential amplifier. Small signal model. So let me draw the same here again. We are keep on drawing the same differential amplifier again and again. So M1 transistor and M2 transistors, and here we are talking about small signal. So small signal definitely have the two component. One is DC to bias your transistor, and then V input one, or you can call it as VG1, right, connected to ground. And then definitely here we have some current called as ISS connected to ground, and this one is referred to be positive and negative. This is VCM plus VG2. So this is the node 1 you can consider, this is the node 2 that you can consider, this is RD, this is also RD, and both are connected to your VDD terminal. And here we have output nodes, which is referred to be this one with a DC VD, with the AC V01, with a DC here which is VD plus V02. So we are considering both DC component as well as AC component together. And if you talk about differential output here, then what you can see is the differential output is something like this. So your positive and negative, this is your VOD differential output. Okay. If we write small signal, then what I can write it as ID1, which is equal to ISS by 2, that is the DC current, plus GM into VID by 2, it's a small signal current. Similarly, if I write ID2, which is equal to ISS by 2, DC component, minus, because our second input, which is the 180-degree phase shift of your input, that's why you'll get minus GM VID by 2, and VD1, which contain both DC component and AC component. So VDD minus RD times, what I can write is ID1 here. So ID1 is ISS by 2 plus GM into VID by 2, right? And VD2, which is VDD minus RD to ISS by 2 minus GM into VID by 2. Now, if you look at this expression carefully, this ISS indicates your DC components, right? And GM times VID by 2 indicates AC components. So we are writing both AC as well as the DC components together. Okay. Now, if we make AC equivalent circuitry for this given differential amplifier, now we are trying to make AC equivalent. So for AC equivalent, what you have to do is DC component goes to 0, DC current source goes to 0, DC component goes to 0, and VDD also goes to 0 time. So what you can see here is, now the resultant circuitry is becoming something like this. Now if I draw AC equivalent model, AC equivalent circuitry, then what you can see here is that the resistor, and here the resistor and second transistor. So this is connected to ground because it is connected to VDD, and this is also connected to ground. This is RD and this is also RD, right? And both the source are connected to current source. Now current source is connected to ground, and this is the point is referred to be virtual ground point. Okay. And here we are applying the AC signal. So we indicate only the AC signal here. This is our AC signal, and here we also indicate the AC signal. This is your VG2, and this is referred to be your VG1. Okay. And definitely here we have VD1 and here VD2 AC components, not DC component. And difference of these two, again AC differential component, which is positive. So here it is negative and this is positive. VOD differential AC output, right? So this point is referred to be virtual ground. And what you can write it here is that for this circuitry, what you can write is I naught 1 with respect to current, then it is GM times VID by 2, I naught 2, which is minus GM times VID by 2, V naught 1, which is referred to be GM times VID, that is the current into the resistor called as RD. V naught 2, which is GM times ID by 2, and it is negative sign, right, into RD. And V naught D, which is differential output voltage for analog. For a small signal model, this is V naught 1 minus V naught 2, which can be written as, and next if we write the differential output gain AD, which is VOD by VID, which can be obtained as GM times RD. Okay. Now this is what we can write from the expression point of view, but we try to draw a small signal equivalent model, and then we'll see what actually the gain of your circuitry. So let's draw a transistor equivalent for M1 small signal model. For this transistor, draw a small signal equivalent model, and for this transistor, draw a small signal equivalent model. So if I draw it, here, then what I can see is that here I have a transistor. First transistor, its gate voltage, and here we are applying the VG1 positive and negative, and as a result of that, here we have a current which is referred to be GM times VG1, and this is the drain terminal and this is the gate terminal, and this is the source terminal of your M1 transistor. And what is the input connected to this M1 transistor is VG1, right? And if you talk about in terms of differential input, what I can write it as half VID, differential input. Okay, and this is what the input signal and then transistor. Now we have one more terminal which is referred to be drain, and drain terminal is connected with the RD resistor. Now where I can write it as RD can be written as somewhere here, not here, then let me write it here, which is RD. And if I include a channel in the modulation factor here, then I can write it as this is R0 and this is RD, and this is connected to ground, right? And this is referred to be my V01. Similarly, if I write it here, let me consider this is my gate terminal, gate, and this is the source, positive and negative VG2. Because of that, there is a current in your circuitry which is referred to be GM times VG2, and here the input we are applying is half VID, minus half VID, because it is a 180 degree shift in the signal, and then correspondingly here we have R0 value, right? And then resistor is there, which is RD resistor, is referred to be RD, and it is connected to ground. And definitely here we have V02, right? Now both the sources are connected virtual ground, so then you just take both the source terminals with virtual ground. So this is your source terminal connected to the source terminal virtually ground. So you can consider this is a ground terminal that you are connecting. This is what actually the small signal equivalent model for the differential amplifier when you are applying the differential input called as VID at this transistor and VA minus VID at this another transistor. Okay. Now what is the AC input for this small signal model? So what you can consider input AC signals. What is VID? VID, which is VG1 minus VG2. Okay, I naught 1, which is referred to be GM times VID by 2, and I naught 2, which is equals to minus GM times VID by 2. Right? What are the output component that you can write it as output AC component as V naught 1 is minus GM times VID by 2, right? What you can write is V naught. So this is a voltage across this two terminal. Let me consider with another color. So this is your V naught 1. So V naught 1 is the two resistor, which these two resistor, these are going to be in parallel along with the current which is flowing in it. So what you can write it as minus V naught 1. V naught 1 is equals to minus GM times VID by 2 into the resistor RD parallel with R naught. Similarly, V naught 2 is plus GM into VID by 2 RD parallel with R naught. Right? Now, if you take the differential output VOD, which is V naught 1 minus V naught 2, V naught 1 minus V naught 2, and which results into minus GM times R naught minus GM times VID into RD parallel with R naught. Right? Now if we take the VOD by VID, which is referred to be AV, is equal to minus GM times RD parallel with R naught. This is the final gain of your differential amplifier with small signal model. But whereas the previous one, we have considered only this part, which is minus GM times RD, but now the actual expression for your differential amplifier with your differential input, which is minus GM times RD parallel with or not. Right? So this is all about your what do you call operation of your differential amplifier with small signal equivalent model. Okay. Now what you can do is you can consider the differential input and then single-ended output. You can take only one output at V01 or V02, and then you take the gain. Right? So these things you can do it at your own disposal. So what you have to do is, or else you can get the same expression by considering the same two parts. One is first part, which is V01, and second part, which is V02. Take individual circuitry, right? And then you try to analyze your V01 and V02, and then combine the V01 and V02, and finally you will get the same expression. That is what this VD which is equals to minus GM times RD parallel with R0. You will get the same expression. That is what we derived just now. And this can be obtained by considering the concept called as half circuitry concept. Means take the half of the circuitry and analyze it output. Same again, take another half of the circuitry and analyze output, combine these two, and finally get the differential gain, which is same as the combination of these two when you have single circuitry, right? And you can also do the single-ended output and then double-ended output for the calculation purpose. So what you have to do is at the home is you can consider that single-ended output analysis and apply the concept of half circuitry. Half circuit concept you apply, just take the half of the circuitry and then analyze the performance. Single-ended output, and then you can also go for differential with double-ended. Okay. So at home you just go with calculation of your single-ended output and then differential output. So where you can apply the formula where the calculation of AV, which is equals to minus capital GM into R out, you apply this formula and you can analyze the performance of your single-ended output circuitry, and you will end up with getting the expression for your AV. Okay. So with this, we can say that the analysis of your differential amplifier and its concept is almost discussed and analyzed, and there are some of the problems related to this differential amplifier, so you have to go through it. Okay. Now we'll talk about the current mirror circuit. For this, the other section people need to be joined. So let's wait for 5 minutes, and we'll join. We'll connect this section B people here, and then we'll start the session. Kartikeya, send me another link for section B.
Sir, for section B also same link, sir.
Same link.
I mean, the previous one, sir. Like previously, this is two links, sir.
Same link. Let me check it.
I'll send the link again, sir.
Um, Kartikeya, no one is there in that link. Inform the others to join it immediately.
Okay, sir.
Yeah, we'll start the session again here. Okay, Kartika, is it audible and visible?
Yes, sir, it's audible, sir.
Okay, screen.
Yes, sir, visible, sir.
Okay, thank you. Now we will talk about the another concept is referred to be our current mirror circuit. So far we discussed about the differential amplifier and then cascade amplifier and single stage amplifiers, right? Now we'll move on to another discussion referred to be our current mirror circuit. Right? So in our IC applications, we are going to use so many current sources and current mirror circuitry as the application demands. Okay, let me draw common source amplifier with uh, ideal current source, which is referred to be something like this. This is ideal current source, and then here we have driving driver transistor, and we apply the input here, and we'll tap the output this location, and then this is your VDD, and this is referred to be your ideal current source that we are talking about. Okay, so this can be replaced. This ideal current source, we what we have done is this was replaced with different configuration with resistor, diode connected load. So you can make this circuitry using a MOS transistor by biasing it, right? So how do you connect it? You just take a MOS transistor and bias a transistor. So let me consider this is M1 transistor, and this M1 transistor applying with input V in, and M2 transistor is replacing your current source, ideal current source, which is connected with the VDD. Now, what you can see here is that this is your common source amplifier, and this is the ideal current source replaced with a practical MOSFET, which is M2. Definitely here you have a V out. Okay. So what you can see here is that this MOS transistor is acting as an amplifier with the current source which is required something like this, and if you have this kind of configuration, ideal current source as a load and then MOS transistor which give you the maximum gain, which is referred to be AV minus GM times R naught. Okay, now we are replacing with the practical MOS transistor which are available because it is very difficult to create an ideal current source. The similar node, what you can also draw is that for a PMOS transistor also. Now consider this is the PMOS transistor with input V in applied. This is the PMOS with V input applied and current is coming inside here. And then you are trying to bias it, which is VB connected to ground, and this is your VDD, right? So this is referred to be your PMOS transistor, and this is referred to be your NMOS transistor, and now this is acting as a current source. This is acting as a current source. Okay, so we are replacing the ideal current source with a MOS transistor. Okay, so these are referred to be current sources, and this current source current must be constant. It should not vary with respect to variation in any other parameter, or it should not vary its current with respect to variation in your temperature, variation in other parameters like noise and other effect. Okay, so what we are doing here is that we are trying to bias these transistors with a voltage called as VB and VB, and will make the current source here. Current source nothing but it should give the constant currents, right? So how to bias these transistors with VB voltage and where the bias voltage is coming from? So that let's say if there is no change in your VB, and then the current, the constant current across this M2 transistor in this picture, and the current in this picture must be same. Not must be, it must be constant. The current that you are expecting from this the two configurations should be constant. It should not vary with any other value that is there in your circuitry. Okay, so you have to generate the constant current. And we have to know that where this biasing is coming from, VB voltage, where this VB voltage is coming from, and then how to give this voltage so that it acts as a constant current and it should not affect the variation. Okay. Then how to bias it. Okay. Now, what I can write it, let me take a pretty simple MOS transistor here, or else what you can write it is problem of biasing current sources. We write it as problem of biasing current sources. Okay, let's take a pretty simple NMOS transistor, and then this is the gate voltage that you have to apply. So now you have to ensure that the gate to source voltage VGS should be, you know, higher value, and then here you have to provide the VB biasing. That VB biasing should contain the DC component, and you ensure that the current which is there here, the drain current ID, should be constant with applying this VB voltage. So what is the relation between these two? Okay, the relation here is that this VB voltage is a gate to source voltage. Now this is connected to ground. VB is your VGS value. As you fix this VB value, then your current is going to be fixed, and then we are well aware that expression of your ID, because we are using the MOS transistor here, ID, which is equivalent of half mu n COX W by L. Now it is VGS minus VTH whole square. So what we are doing here is VGS is replaced with the biasing voltage called as VB, right? So VB voltage, which is coming from somewhere, and then it defines a current called as ID. There is a MOS transistor current, and this is a non-linear expression. This is not a linear expression, right? Now, when you look at this expression, and the voltage which is coming here, now you can replace the VGS, which is equivalent of VB. Now you can write it as VB minus VTH whole square. Now, if we look at this expression, what you can notice is that the term called as mu n is a mobility of a transistor, and VTH is a threshold voltage of the transistor. So these two factors varies with temperature. Am I right? When you vary the temperature, then definitely the mobility of your material going to be changed, and then threshold voltage of the device is going to also change. It means if these two factors is getting modulates, then your current is getting modulates. Okay, even though you fix a value of VB, right? Because you expect that once you fix a value of VB, then your current must be constant, it should not change. But from this expression, what we are noticing is that as we are fixing VB value, then when we see the current expression of this MOS transistor, then mu n value is variable with temperature, and then VTH value is also varies with temperature. Now, if these two factors changes, then definitely ID is not going to be constant. We are calling it as it's a constant current. This current is not no more constant if temperature changes. You can take a best example that some of you may be sitting at your home, maybe in some ACs or somewhere where the cool place. The temperature around you is close to 30 or 30 or 27 degrees, whereas when you are going outside, then the temperature is close to 40 or something. So when the temperature is difference of 10 degrees, now you are at a home or somewhere, then your temperature is, let's say, 30 degrees or less than 30, but outside of your house and then on the road, you can see the temperature is close to 40 degrees. When there is a variation in temperature, definitely there is a variation in current takes place because the device is made up of material, which material is sensitive with the temperature. Right? So definitely mu n is not going to be fixed. Mu n changes as temperature changes, because your device, you are using the same device, let's say mobile phones in your home, and then you are going outside, then the temperature is going to be varies. As temperature varies, then your current, the constant current that is there in your integrated circuit in your mobile phone is going to varies. It is not constant. But what you are talking is that the constant is the current ID should be constant as VB is going to be fixed. Okay, so this is referred to be one of the problem while biasing your constant current source. Even though we fix the value of VB, but the transistor which normally not generate the constant current, and it varies with the temperature variation. Okay, so you can consider this is a problem. This is one of the problem, and we can call it as a problem one. What is the problem one? The current is no more constant because the variation in temperature causes to be variation in mobility and threshold voltage of the device, which results into variation in the current. Okay, in a system implementation or a complex circuitry implementation, there are multiple current sources are there, not a single current source. Let's say you have a complex IC and which contains tens and hundreds of your current source, and all these current source may be same or may not be same. You cannot say that all current sources ID value is same. It need not to be same. Here ID1, another at ID2, and at another place it is ID3. There are hundreds and hundreds of current sources, and all these current sources are different. Okay, and VB value, let's say if you are fixing with a battery, okay, VB value is you are fixing with a battery, then battery value, no, battery is no more constant because as time progresses, your battery is going to be dries. So battery voltage slowly drops, and then as a result of that, VB is going to be varies, and definitely your current is going to be changes. Okay, let's assume that mu and VTH is one of the factor that influence the current. Another factor is that the VB value. This VB value is applied with some battery, right? Let's say it's a DC battery. Now this DC battery is no more constant because once you charge it, and then slowly as time progresses, it is going to be discharged. Let's say it is 3 volts, and after 1 to 2 hours, now it is become 2.7 volts, and then after it becomes 2.5 volts, and as so on. Your battery is going to be drops the voltage slowly, and then it comes to the 0 volts. So as the voltage is not going to be fixed, then you cannot generate the constant current. Okay, so in case of multiple current sources, what we normally do is we'll take a single battery, and then how do we provide the biasing for it? We provide the biasing for all different VB values. So somewhere you required VB1, and another place you required VB2, because you required ID1, ID2, ID3, and then ID5, and hundreds of IDs you required, and as a result of that, you required hundreds of VBs. So for hundreds of VB, will you use hundreds of batteries for that? So we are not going to use hundreds of battery. We use single battery, which is very higher in voltage level, and then we use a potential divider circuitry or voltage divider circuitry, and then we provide the VB1, VB2 as it requires. So what we are trying to do here is we'll take a single battery, and then we use a potential divider circuit as per your current source bias voltage requirement. We use the voltage divider circuitry and we apply to that, so that what we can achieve is that the current which is ID1, ID2, and ID3 as the current constant current that we are expecting, the same current we can obtain with single current with single battery and potential divider circuit, right? So the construction of that is going to be something like this. Let me draw the construction here. So let's basically we use a MOS transistor as a current source, obviously, and this is our NMOS transistor connected to ground, let's say, and here we are expecting that the current ID should be constant, and here we require the voltage VGS, right, or VB voltage that you are talking about. This is the VB voltage that we are talking about. And how do you apply this VB voltage? We are taking a battery here, right, called as VDD, and we apply a potential divider circuitry here. So this is R1 and this is our R2. So voltage across R2, which is given as R2 divided by R1 plus R2 into VDD is your VB voltage. So voltage across R2 is equivalent of your VB. Now you use this battery which is called as VDD, and then apply the potential divider circuit, something like this, so that you can achieve the current here, and this current is referred to be ID, which is half mu n COX W by L. Now VB value is modified as R2 divided by R1 plus R2 into VDD minus VTH whole square. So I can write the same here, which is referred to be R2 divided by R1 plus R2 into VDD minus VTH whole square. This is what the current that we are talking about. Now, here you have the battery. This battery is also not fixed value. It is going to be varies as the time is going to be progresses. Okay, so this is called as supply dependent. The current is depends on your supply voltage, because as battery dries, then this VD value drops, and then finally you will not get the constant current that we are talking about. Right? Now we are talking about biasing here. In the biasing, we are trying to provide a VB, and we try to get the ID value should be constant, but we are not getting the ID constant because one problem is the temperature changes and other problem is supply voltage dependent. So this is referred to be your problem number 2 while biasing. Okay. So we have to make sure that the current ID which we are trying to generate ID that should be constant. But what is happening here is that because of temperature and then supply dependent, this ID is no more constant. Okay. Now what we have to do is we have to create a bias current which should not depends on the temperature as well as your supply, right? This is the main object of your current mirror circuitry when we are trying to implement a current mirror. So you have to bias the circuitry. That biasing should not depends on the temperature as well as the supply dependent. And considering these two problem in a mind, and then we try to start building the current mirror circuits. Okay, current mirror circuit nothing but we have to generate a constant current. That's it. Okay, and how do we start with generating a constant current? We'll try to use reference current first, and then we try to replicate the same current. Okay, so what we try to do is we try to take the concept of current mirror. What we try to do first is that we have to build a constant current. First thing what we have to do is we have to build a reference current that is referred to be a golden current source, and this golden current source is temperature independent and temperature independent as well as insensitive with the supply voltage. And there are different methodologies and wayouts. You can generate a golden current source, or you can call it as a reference current source, or you can call it as ideal. Okay, how do you generate these sources? There is a specific circuitry called as band gap circuitry. This band gap circuitry will generate a golden current source, and this golden current source is not going to vary with temperature as well as the supply voltage. Somehow we'll try to make some current source a reference current source, and then we try to generate the same current as the golden source current using the transistors. Okay, right? So we have to use transistor, and then how we try to get the current in a transistor is just like the golden current source. Okay, that is what the challenge that we have now, and we have to handle it so that the current which is coming into the transistor ID current, that should be same as the golden current or some reference current, and that reference current is getting from your band gap circuitry. There is a specific circuit or equipment which generate some reference circuitry. And second step what we have to do is, if you are able to generate this, then you just copy the golden current or clone it. Copy the current or clone the current so that you can generate many current sources. Okay, Let's say you have reference current, I reference, and then you just clone the I references and try to generate I1, I2, I3, I4, and I5 as per your requirement. And this I1 to I5 or I10, all these are same as that of your I reference current. And this I reference is independent of your temperature variation and then supply variation, right? That is what we try to do it now. So let's take a reference current source, which is referred to be a golden current source. You can call it as there is some circuitry with generating golden current source, right? There is a golden current source, something like this, and now we required some currents. So here you can write it as golden. We required some currents. Let's take this is the current I required here, and we required one more current here. So this current I2 and this is I1. So this I1 is same as I2, same properties, and then I2 is also same. It does not mean that equal value, maybe variation in value, but the property of your I1 should not affecting with variation in temperature and then supply voltage. Similarly, the I2 also. Okay. Then what we have to do, definitely we have to use a MOS transistor, and MOS transistor can generate the current. So what we need to do is just take the same reference current here. So this is where you are having the golden current source. And now what we have to do is just take a MOS transistor here, and MOS transistor connected to ground, and here it generates a current called as I1, right? So this I1 current is the current which is generating from your band gap circuitry current. So now this current is independent of all the problem that we are talking about. So to generate this I1 current, then what we have to do, we should require a voltage which is at the gate terminal. We call it as VB voltage, biasing voltage. This VB voltage, V biasing voltage, should have the information of this golden reference current source. Then only we can generate the I1 current which is same as that of your golden source current. So this MOS transistor is supposed to have the information of the golden current source, and that is applied to this transistor so that the I1 current is similar to that of your golden source current. Okay, means the biasing voltage that we have to apply here should have the information of this reference current source. Okay, so how to make the information of this golden current source to the biasing voltage of the transistor? What we have to do? We don't have other options. We have the only option is that let's consider this structure again. So here we have the MOS transistor. Let me take this is reference current source, I reference. Okay, and here we are trying to generate a current called as I out or I1. Let's take it is I out. Now this I out, right, is connected to ground, let's say. Now we have to provide the information to it. Then how do you provide the information? Just connect a resistor here and we connect this terminal to your transistor. Now this is referred to be resistor R. Okay, and this is your I reference current. Now what we are expecting that this I out current is same as the I reference current properties. Okay, now if I write I out expression, which is half mu n cox w by L VGS value. So this is your VGS value. This VGS is voltage across the resistor R. So what is voltage across resistor R? Which is equivalent of VR, which is equal to VGS is equivalent to I reference into R. So now this is your VGS value. Now we are going to substitute it, which is I reference into R minus VTH whole square, right? Now what you can see here is that the term called as R, term called as mu n, and the term called as VTH, these three factors again temperature dependent. When once you take this resistor here, the resistor is temperature dependent. Of course, in the previous expression where we have potential divider circuit, there also we have resistor R1 and R2, and it also depends on the temperature. Along with that, there is a voltage is getting added in it, right? Now all these three parameters which varies with the temperature, and this is not a good sign to execute our problem. Then what we have to do is let's go with another way around and then how to tackle this problem. Okay, so what we have to do is we have to apply some biasing voltage. That biasing voltage should be, avoid the mu terms and then threshold voltage term and then resistance terms. Then how to get it? Then what we have to, what we have to do is just take, you can call it as the trial one, first trial. Okay, what we do is we take a MOS transistor and what we're trying to do here is that connect the MOS transistor gate with drain terminal. Now it become a two terminal device. This is the drain and source, gate is connected to drain. So it become a two terminal device. Now we apply a voltage across this transistor. Now this transistor is becoming a diode connected device. Diode connected equivalent MOS transistor. So now we apply a voltage V, positive negative here, and as a result of that there is a current called as I1 into a transistor. When you plot the ID VGS for this diode connected MOSFET device, then this is a V. Now we can measure the voltage across this transistor, which is referred to be a V1, because there is a current which is I1 flowing into this diode connected MOS transistor, and as a result of that there is a voltage across this diode. So we call it as V1 and current which is I1. Okay, if the MOS transistor, this transistor is on and in saturation region of operation, then what you're going to see is that the current that is flowing into the MOS transistor called as I1, which is half mu n COX W by L. V1 is a voltage across this device because the gate and drains are connected together. Gate to source voltage equal to drain to source voltage. Both are same here, that is V1 minus VTH whole square. With this expression, if your V1 is very less value, initially V1 is very less value because V voltage, as you vary the voltage V here, and correspondingly there is a variation in V1. Now we are plotting V1 and then I1. So as your V1 is smaller value and it is up to VTH, threshold voltage of the transistor, because it is there in your expression, up to VTH there is no current in your device, but beyond VTH then you see that there is a current across a MOS transistor, right? This is what you can notice, right? And here V1 should be greater than or equals to VTH, then only you can see the current. Okay, now we are applying voltage here. Now, instead of voltage, what we are trying to do is we are trying to make the biasing here, right? Now if we apply a current and then we can take the voltage also. So how do we make that configuration? What we'll do is, let's try diode connected MOS transistor again. This one, two terminal device. Okay, now we try to apply a current source here. And now we are considering that this is a diode, and across the diode we are applying a current called as I1, and because of the current there is a variation in your voltage across this MOS transistor. So this is your M1 transistor that you have. Now if you make a plot here, this is a plot which is with respect to I1 and this is your V1. Previous case it is exactly reverse. Now x-axis is a V1 and y-axis is I1. Now x-axis is I1 and v-axis is a V1. So I1 is a current source that we are applying or varying the current, and as a result of that there is a variation in the voltage across your MOS transistor M1, right? So what you can notice here is that as your current is 0, then what you can see that now from the above expression, this one, you can easily identify the value of V1. What you can notice, V1, which is equivalent of, now you take this term this side and then you rearrange this. What you can end up is that, which is 2 times of I1 divided by mu n COX W by L plus VTH. This is what you can notice the current expression. The same current expression, if you write it here, which is V1 is under root 2I1 over mu n COX W by L plus VTH, right? Now your current is 0, then what happens? This term is going to be 0, then V1 is equal to VTH. So you have some current, some voltage that is referred to be a VTH voltage, right? As your current is exceeding just greater than 0, then you have a variation in your voltage, and that variation is going to be something like this. So once you notice these two figures, the I1 versus V1 and V1 versus I1, so this is exactly the 45-degree phase shift in the curve. So what you can say that if I take a line here, something like this one. Now if I rotate it 45 degrees here, then you can see the previous plot, and the previous plot, if you rotate it 45 degrees, then you can see this present plot. Okay. So here V1, which is referred to be the biasing voltage that you can consider here across the transistor. Okay. Now we can see that this V1 voltage that we are well known, and then we apply this one to a transistor, then how the configuration is going to be. Let me modify the configuration here. So this is our MOS transistor which is required to bias, and it requires a voltage called as VB biasing voltage. So this is the VB biasing you required for a transistor, and this is your M2 transistor. Okay, and we made a certain arrangement, and we identify the value of biasing voltage which is V1, right? So how do we have we made this V1? V1 is made with the help of a transistor which is acting as a diode connected load, diode connected MOS transistor, and it is biased with a current source. So here we have a current source, something like this is connected, right? Now here the current is I1 and voltage across here is V1. This voltage is same as this VP. So this is the VB voltage that you are talking about. So there's a VB which is equivalent of V1, right? And just now we constructed this circuitry, and then we applied across this gate to source voltage of your circuitry, and then finally we try to check that what is the I out current that it can generate, right? Now if we write expression for I out here, which is half mu n COX W by L. Now this is your M2 transistor. Let me consider this is my M1 transistor. So W by L of 2, second transistor it is, right? Into V1 minus VTH whole square. What is V1? V1 is this one. So you have to substitute V1 expression here. So what I can write it here is that I out, which is equal to half mu n COX W by L of 2 V1, which is under root 2 times I1 mu n COX W by L of first transistor, because this is a transistor and its voltage we are talking about, plus VTH minus VTH whole square. Now if you look at this expression carefully, this VTH and VTH gets cancelled out. The square is there, then square gets cancels the root, right? And you end up with this square and roots gets out, and then 2i by mu n COX W by L1 into half mu n COX W by L2. So here 2 and half gets cancelled out, this mu n COX gets cancelled out, and here mu n COX gets cancelled because this mu n COX at the numerator and this is at the denominator part, and you end up with I out, which is equal to W by L of 2 divided by W by L of 1 into I1. Now if you look at this expression carefully, what it tells you? It tells that this I out current is the current that we are talking about, this I out current, which depends on the W by L ratios and I1 current. I1 is the reference current that we are generating from band gap circuitry. That is fixed, it is not going to be changed. W by L value is independent of your temperature as well as the supply line. Now we came with a current that is generated with our circuitry kind of setup, which going to gives us the current which is independent of temperature as well as the supply voltage, is something like this. Okay, now what we have to do is we just remodify this structure and then let's see how it is going to be. If I1 current is good, then definitely it results into, if I1 is good, then definitely I out is also as good as I1. Then the ratio of W by L of M1, M2 and M1 gives your I out current, right? So it is independent of the other factor that we are talking about. Now let me rearrange this structure again here. So this is what the M2 transistor that we have. Let me consider this one. This is I out current that you can call it as. Now here, instead of this NMOS transistor, we try to use again we use NMOS transistor only, but we modify this orientation and then see how it is going to be. Now if you go back to this discussion, then what had actually applied here is this is your gate to source voltage, which is your V1, right? And then this current which is entering at the drain terminal of this diode connected transistor. So the same arrangement that we will do here, what we do is, this is the current which is I reference current, golden current, which is coming from some source, and it is entering at the drain terminal of a MOS transistor, this one, and this transistor drain terminal and gate terminals are connected together, right? So this is the VB voltage that you require for the transistor to generate I out current, which is positive and negative. So this is connected to ground, this is VGS, which is equal to VB terminal, and what we have to do is we just act so the voltage is VB. This is what the modified structure, not modified, simplified your ID I reference is entering at the drain node. This is the drain, this is source and the gate and drain shorted together to act as your diode connected device, and I reference entering at the drain node, and remaining things are same. Now this I out, which is referred to be, this is your M1 transistor, W by L of 2 divided by W by L of 1 into I reference. This is what the current that you can see, and which is independent of the all the factor that we were talking about. Okay. Now, if you want to make I out is equivalent to I reference, then what you have to do? What you have to do is just select W by L of 2 is equivalent to W by L of 1. Then I reference is equivalent to I out. Now you want to make I out, which is equal to twice the I reference. Then what you have to do? Select the W by L of 2 in such a way that your I out current is double the I reference current. Or else, let's say you require the I out current which is half of your I reference, then what you have to do? Select the W by L of 2 such a way that your I out is equivalent to I reference by 2. So what you have to do, you just play with W by L ratios of your transistors, which is M1 and M2, and then you can generate the current I out that could be same as your I reference, twice of the I reference, half of your I reference, or multiple times of your I reference that you can generate. Not only I naught, you can also make the circuitry something like this. Let me construct a circuitry here. This is I reference. This is connected something like this, and then this is referred to be I1 current. This is your M1 transistor and this is M2 transistor. I require another, then what I have to do is just I take one more transistor which is M3, okay, connected to ground, and then I bias this transistor from this point in such a way that this I2 which is equal to twice the I reference. Okay, you can make any value of n with respect to your I reference current. Likewise, you can take I3, I4, and I5 as many current sources, as many current mirrors that you require. Then you can take that many current mirrors and you try to design it. Right? This is what the concept of current mirror circuitry that we are talking about. Okay? We'll see the problems related to current mirror circuits in the next class. If you have any queries related to this, then you can raise a question. Okay, if there is no query, then CR from both the section, please give me the attendance. And we'll stop the session here and we'll meet in the next class.